Alright, video 2. Am I really going to go through all of these? Sure. Let's do it. We've got a puzzle. It's kind of fun. If we were in class, these can actually be fun. You got to figure out what X, Y, and Z are. They are problem-solving puzzles. So use the evidence. We've got a diameter, which means this is 180 degrees and this is 180 degrees. So there's how we can solve for X. X has to be 30 to make 180 degrees here. Z is the inscribed angle for this arc, which is half. So Z is 15 and Y is half of 50. So Y is 25. Sorry if that's small and you can hear me say it. X is 30, Y is 25, Z is 15. 23. And I encourage you to pause these and do them for yourself before you just watch me do it for you. One thing here, I see a triangle, so I can go ahead and say that this is a 55 degree angle, making 180 degrees here. Now, we're just use theorem 10.7. It says if you got yourself an angle inscribed, then the arc is double in this case. So that's 120. It's 165 times 2, 130. And this is 55 times 2, 110. What do you get when you add 110 plus 130 plus 120? 360, that's what it should be. 24. This is a good old theorem 1010, which says in an inscribed quadrilateral, opposites have to add up to 180. So that makes this 110, 180, and that makes this 100. And then, to solve for Z, Z gets a little tricky. For Z, we're going to use angle X. Angle X is inscribed with this arc. Because that's 110, that makes this whole arc have to be 220 because it's double. And if this is 120, then that makes this 100. Because 100 plus 120 makes 220. So Z had to be 100. 25. There's theorem 10.7 again. We have a arc with an angle, so it's doubled. There you go. Y was easy. X was easy as well because, again, theorem 10.7. I like theorem 10.7. Straightforward. The angle is half of the arc. And how are we going to figure out what Z is? To figure out what Z is, you got to use this angle. So add it up, subtract from 180. $55. That is also 55, which makes this 110 as well. It ended up being an isosceles triangle. 26. And the camera is still rolling. Good. More of the same. So we have an isosceles triangle. Start with 180 degrees in your calculator. Subtract 50. And divide that into two equal angles, so that's 65 and 65. I guess this time we're starting with solving for Z. Also, because this angle has this arc, that makes this a 100 degree arc. And now use theorem 10.11. If you got a tangent and an arc, the angle is half. So that's 50, X is 50. And lastly, because of the 65 here, this is going to be double 65, which makes this 130. 27. We got a diameter. So this is all about theorem 10.9, which says if you got a diameter, this is a right angle, this is a right angle, and this is a right angle. If you are inscribed with a semicircle, that makes 180 degrees, which makes this 90. Alright, those are more of the same. Do them. I'm running out of room on my video. I only get 20 minutes, so let's keep moving forward. These are just more angle problems. 31. Now we're getting into some segment length problems. These were all angle problems, angles and arcs, and the rest are going to be segment lengths and stuff like that. So 31, so we're gonna transition to these last three theorems for the segment lengths. This is theorem 10.14, which says A times B equals x times y 9 times 16. So you're going to have to set it up like that. So x squared equals 9 times 16, 144. The square root of 144 is 12. 32. Basically, we're using theorem 10.16. You're going to do outer times the whole length. In this case, the outer part is the whole length. So you're going to do outer times the whole length equals outer. And what's the whole length? The whole length is 7. That's the relationship. These proofs are really cool if you want to try to attempt to prove that is the case. This is not going to be a pretty answer, so we'll just keep this as the square root of 21. Actually, square root of 21 is about 4.6. So if you put 4.6, that would be fine for that. 33, same idea. This one looks a little bit more like theorem 10.15, which is the same idea. It's outer times whole. The outer part times the whole length equals outer part times the whole length. So in this case, we're going to do 3 times the entire length, 8. Outer length times the entire length. Now what's the entire length of that? 2x on the outside, x on the inside, so the entire length is 3x. Alright, so let's see here. What do we got? We got 3 times 8, that's 24. We got 2 times 3, which is 6. And we got x times x, which is x squared. So that's all that put together. Divide. You're going to get 4. You're going to get 2 as your answer. Alright, 34. This one got a little tricky. Let's see what we got here. This is going to be theorem 10.14. A times B equals x times y. So let's take a look. We have A times B equals x times y. Now how long is this length? Well, if the radius is 6, that makes this 6. So this whole length here is 6 plus 3, which is 9. Do a little work there. But here we've got x squared is equal to 3 times 9, which is 27. So x is equal to the square root of 27, which, if you do a little work there, you end up getting 3 root 3 is the answer for that one. 35. Kind of run out of room here, but it's alright. Got extra work, extra room here. We're going to do outer times the entire length equals outer times the entire length. They tell you the entire length is the x in this problem. So that's just 40 equals 5x, x equals 8. Let's skip 36. It's got fractions. Come on. Last problem is 37. And here we go. Same idea. Outer times the entire length equals the outer part times the entire length. If this is x and this is 3x, the entire length is 4x. Alright, let's work this out. This is 100 equals 4x squared. Divide the 4. And get x is equal to 5. Alright, a couple of other things to consider here. Put at the bottom. Inscribe versus circumscribe. So here I've got, because the triangle, the vertices hit the circle, each vertex hits, unlike this one. Okay, so here in this picture we've got a triangle inscribed in a circle. This triangle is not inscribed. It's inside, but it's not inscribed. Or another way to think of this is the circle is circumscribed about the triangle. In this scenario, the circle is not technically circumscribed. So it's inscribed versus circumscribed. We have an inscribed triangle, we have a circumscribed circle. Tangent versus secant. This line is tangent, intersects once. This line is secant, it intersects twice. Tangent means to kiss, secant means to cut. It's cutting through the circle. Inscribed angle versus a central angle. If you draw an angle from the center, you get a central angle. And if this is, say, an 80-degree angle, then this is an 80-degree arc. What if you make an inscribed angle? An inscribed angle, it's on the circle. This is an 80-degree arc, which makes this a 40-degree inscribed angle. So central angle, inscribed angle. Angle arc theorem versus segment length theorem. Alright, so if you look at your theorems, 7, 8, 9, 10, 11, and 12, and 13. So all of these are dealing with arcs and angles. And then these last three are dealing with segment lengths. So what's the difference between 1013 and 1015? Because they look like the same picture. This picture looks like this picture. The difference is this theorem is about the arcs and the angles, and this theorem is about the lengths of these segments. So make sure you understand arc-angle theorems versus segment length theorems. Alright, that's all I need to say about that. Your homework is to complete the review. You can skip the problems that I skipped, that's fine. Take a picture and submit it. Happy studies.